video for week 7 because you have your written assessment. So what have we got here? So if the differential equation is not linear, or even if it is, so the linearity of the differential equation is kind of a technical thing, which I didn't fully explain. But I think it's something like the thing up in orange in the top right hand corner that I think, and I'm actually not 100% sure on this because the external force complicates things, but roughly something like this, that if you have two solutions, if you have a solution you can multiply by a constant and get another solution. I know that actually doesn't work if you have this 5x external force. But don't worry, in terms, like, I'll only, actually, let's look at this one. Is this linear? This one is linear because it's 0 on the right hand side. Is that right? No, it's not. There's a constant. We won't worry about it. I can definitely say when something isn't linear. For example, this power of 4. So that's not linear. Okay. Anyway, so if the differential equation is not linear, like this one down here, or even if it is, what we can do, so you're in a boundary value problem and you don't know the initial derivative. So what you can do is just try loads of different values. Now, you can imagine writing code and just kind of messing around. I don't know, really this pathetic, but when I was younger, we had like these caveman, cave person, whatever, cave person calculators where like it couldn't do a square root or anything, it would just do multiplication. I'm not that old. And like a game I would play would be kind of, find the square root of 7, and like, you start with 2 squared, then you like 2.5 squared, like the bisection method you would have done with Bob. So you can do something similar where you just keep adjusting the initial derivative until you get there, until you hit the nail on the head. Now, one way of doing it is using goal seek. Essentially, that's roughly what you can think goal seek does. I know you've done goal seek a number of weeks back in VBA, where it's like, it just tries loads of values. Okay, so let's see how you'd set this up for VBA. So suppose the following: it's non-linear. ODE governs the temperature of a heated rod. Might be more accurate there. So this is what we got. And so first of all, write it as two initial value problems. I don't have that much space there. I have to be careful. Yeah. So you're going to let v be the first derivative. I'll maybe write this bit over here. So let v equal to the first derivative. Now that's some kind of a temperature gradient now. What it represents, it's the rate of change. Yeah, it's like a temperature gradient. Therefore, if we differentiate both sides, the dv dx is equal to the second derivative of temperature. Okay, and that means if I add this kind of second term with the weird thing with the 5 by 10 to the minus 8 and the 20 minus temperature to the power of 4, add that to both sides, I have an initial value problem. So I can say the differential equation for t is dt dx is equal to v, and we put the initial value of t there. T of 0 is equal to 40. And then, as I said, add this to both sides and understand that the second derivative of temperature is dv dx. I have also an equation for v. So you turn the second order differential equation into two first order differential equations. So am I talking 5 by 10 to the minus 8 times 20 minus the temperature to the power of 4. But the thing is, I do not know the initial value of this. So you're not going to do this by hand, like, no way. It's just completely not feasible. So we'll look at doing it in VBA. So let's see. On an Excel worksheet, we solved the problem using Heinz method with a step size of 0.1. So we start with a guess of v of 0 equal to 10. Now it doesn't really matter what it is, but let's see, can we get, whereas I don't think we should really start with 10. A realistic starting value, or a better one, would be something like this. So this is x, this is t, and we've got at 0, we've got 40. And at 10, it is 200. And so like what is the initial V? It's actually the initial slope. So a good idea would be to shoot straight at, think of shooting straight at it. And if you do the rise over the run, so this would be 160 and this would be 10. A reasonable starter really would be 16. Now, it doesn't essentially matter what you use, but 16 would have been probably a bit better. I think to give you a starting thing, you should shoot straight at it. So, or we could have used 16. Now, we're supposed to be hitting 200, but if you do this, it hits 233, which is off. It's an overshot. Isn't it a big overshot? Yeah, we're trying to hit 200. It's not too bad. So it's an overshot. So what we do is we're going to data, what if analysis, goal seek. So you would have seen this before. And what we're going to do is we're going to change the initial value of V0, which isn't coming up here, but it'd be in row 2. It would be this value here. So this was initially 10. So we're going, and this would be in column B, row 2. So we're going to, so you want the final temperature. That's the temperature at a distance of 10. That is, now this must be columns A, B, C, D. So you want D102 to equal 200 by changing B2, the initial value of V. And so you press OK, you'll see it doing this thing. And eventually it turns out that the initial velocity, 9.316, would see it hitting exactly at 200. So if this is 0.40, and this initial slope, which we call V0, is approximately 9.316, you will hit where you're supposed to hit, distance of 10, temperature of 200. So that's your goal seek, and you'll be doing that in the lab in, I think, week 7. Okay, so you can also do it for linear ODEs. It doesn't make as much sense because you can instead, you can take 2 shots and average them using the stuff we did last week. But you can do it here. So what have we got here? Consider a particle mass 200 grams subject to a spring force with a spring constant of 5. What velocity must the particle start off with if its initial displacement is 1 and it's returned to equilibrium for the first time and is 2? Yeah, so this is kind of like design again, really. Like if you want to think about what this is a spring that is supposed to close in half a second. So as usual, convert it to initial value problems. So the first one is so you let V equal to dx dt, and then differentiate both of these with respect to t. And so we have dv dt is equal to, no, not dv dt, well, we'll get to that in a moment. Dt is v. Put that with the initial value of x, which is 1 from the question. And then dv dt is the other one, is equal to the second derivative, which as we can see is minus 25x. This is the differential equation for v, so we should put the initial value of v, but we've no idea what that is. Now, for some reason, I'm picking v of 0 equal to 4. It makes way more sense, I think, to pick v of 0 equal to 0. So let's draw a picture. Here's x. Here's t. And we've got the point. Actually, there's even a different value to pick, really. So here's the initial point, 0, 1. And after half a second, it's at 0. So if you're to shoot directly at it, which makes more sense, do rise over run. So the initial slope should have been, the rise is minus a half, or the run is 1. Really should have considered using minus a half. but it doesn't matter is the point. So if we do it with 4, it doesn't work. But what you can do is do a goal seek. Do a goal seek again. So this, I think, is Euler's method. So this is time. This must be x. This must be v. And C2 is v of 0. This here is x of 0.5. There's something interesting here as well. I think there's possibly many solutions of this. I think about it, but we won't go into that. Yeah, we won't go into that. So we want to B52 to be equal 0. So that's what we're looking for. And we're going to try and get that equal to 0 by changing C2, which is initial V0, and we get it. So what do we get here is, it turns out that V of 0 to 6.664 does the job. So let's draw some stuff here. So in terms of orange, we see at 0, at time equal to 0, the x value is 1. At time equal to 0.5, the x value is 0. Obviously, looking at this graph, if you started from rest, what would happen is it would close too quickly. So it actually, look at it, started going up. So the initial V is positive and is approximately equal to, let's say, 6.7 here. And we get the job done. We get everything that we want to see. Okay, I think that's all I have to say about that. So we've finished the big first chapter. You'll be doing a lab on this after week 7.